Good evening, everybody. My name is Ravi Palaparthi. I'm the founder and principal of Anaga Consultants. We operate both out of India and the US. Today, as part of this webinar, we are going to share our experiences in minimizing trials and errors in product process development in an industrial setting with first principle approaches. A brief note about ourselves. As a small company, we have an experience and expertise spanning process engineering and development in the pharma and specialty material spaces. We are also into the development of scientific computational tools for process modeling. As an outline of today's webinar, we will start off with a couple of example challenges from our experiences that show how the so-called uncertainties in a process can in fact be mitigated by looking at the depth of details of the process. Then we will have an example case study to show how incorporating the process understanding in the scale-up efforts can help minimize surprises. We will follow that up with a couple of strategies that we can recommend for you to consider incorporating in your process development journey so that you can minimize trials and errors in your scale-up efforts. Towards the end, we will have some time for Q&A. As a first example, we will look at the drying of drug-loaded polymeric microspheres in the making of so-called extended release drug products in the pharma industry. Here, the manufacturing process consists of a series of steps upstream which culminate into collection of these polymeric microspheres containing the drug. And along with the drug in the microspheres, there will be a solvent that is used in the upstream steps. Now the challenge is to be able to dry off that solvent so that we can get a free-flowing polymeric microspheres containing the drug. Now, what we have seen are cases where in a lab process, we do get a free-flowing product, whereas in the plant scale, the same drying cycle, if you use the same drying cycle, we may end up getting a hard cake that is very difficult to process downstream. Now, to look at why this is happening, we have to understand a little bit of what exactly is happening in the drying step. Now, the drying is typically done in a filter dryer type of an assembly shown here, where the suspension of the microspheres is loaded and at a low pressure when vacuum is applied, we have a certain temperature controlled by the jacketed fluid. A thermal cycle is applied to evaporate the solvent off and dry the product. As this proceeds, what we need to know is these polymeric microspheres have something called glass transition temperature. So as the solvent content evaporates because of the applied thermal and pressure settings, the blue line shows how the solvent content can reduce over this drying time. As the solvent content reduces, the glass transition temperature of the polymer microspheres can change, can actually maybe increase during the drying. Now, as long as the temperature of the particles, the polymer, is less than the TG, these particles will not stick to each other and they can behave like free-flowing. But when they go above, when the temperature goes above, the product temperature goes above the TG, you get the stickiness and the chances of cake formation increases. So from a process side, what we need to look at is how can we maintain during the course of this drying cycle the product temperature always below the TG at that solvent content at any given time. Now, how we accomplish that is how one of the challenges here is based on the heat transfer, etc. details of the dryer, we should be able to control the jacket temperature to achieve a product temperature that is below the TG. So if we can define the drying cycles appropriately, we should be able to get a free-flowing powder even at the plant scale. As a second example, let's look at a case of manufacture of API crystals of certain polymorphic form and certain size distribution using antisolvent crystallization. This is a typical process used in the pharma industry. Here, an antisolvent is introduced into a solution of API in a solvent. The expectation is, depending on the mixing conditions involved, we create saturation type of conditions for the API to precipitate out. The challenges in this type of a process, as we have observed, can be ranging from not being able to repeatably get the process under control even in the lab scale, and also when we have something, a scenario established where we can repeatably get the required crystal size and form in the lab scale, not being able to translate that into a plant scale, having, say, a different geometry of the vessel, impeller, etc. Now, for us to understand where the sources of the lack of repeatability, etc., are coming from, we need to understand how the mixing, the concepts of mixing, how they interact with the concepts of thermodynamics that actually create this saturation or supersaturation type of conditions. Towards that, briefly, we need to be aware of the fact that when we introduce, say, an antisolvent, say here B, in a solution containing the API, say A, the geometry and the mixing conditions determine in how much time B will disperse in A, and what is the concentration distribution of B like in the vessel. These factors will determine what's the level of supersaturation of, say, the API, or the level of saturation of the API, and accordingly the formation mechanisms of the crystals will be influenced. So how the vessel geometry, the location of addition of B into A, the rate of addition, the liquid level, how all these factors influence the concentration distribution, we need to be able to understand that, and accordingly be able to manipulate the process depending on the changes in the geometry or scales to be able to get the crystals of the right size and the right polymorphic nature to ensure that there are no quality changes as you go from, say, one scale to the other scale, or one vessel geometry to the other vessel geometry, say, even while being in the lab. As a third example, let's consider the case of dispersion of particles using a high shear mixer and stabilizing them with surfactants. This is a typical scenario when one wants to make, say, injectable nanosuspensions in the pharma space, or, say, inks, nano inks in the specialty material space. In either of these scenarios, we have, say, API particles introduced in a continuous phase that is getting sheared using a high shear mixer, while the surfactant is getting added. Now, some of the, if you look at what factors impact the stabilization of these nanoparticles, we're looking at how well the particles are sheared, and the increase in surface area because of either particle breakage or dispersion, how that increased surface area is stabilized rather, by the addition of surfactant. So the balance of these two phenomena is what contributes to getting a good product. Now, typical issues in this type of a process can be, again, a batch-to-batch repeatability within a lab scale, and translating a lab scale process into the plant, where one would use, instead of a batch process, an inline mixer to process the high throughput. Now, what all factors contribute to changes in the mixing conditions when we use this type of a high shear mixer is something to worry about, so that we minimize these repeatability issues. For example, how the mixer, where is it located in the, say, in the batch vessel, and what is the height of the liquid column that is used. All these impact, say, the circulation time of the ingredients in the vessel, and hence how much effective shear is imparted to the particles in a given time. And these things play a role in how well or what differences could exist in terms of stabilization of the particles. In addition, when we think of changing from the batch to the inline mode as part of a scale-up, again, how the shear rate, the total shear can be balanced in these two configurations is important. From the previous three examples, I hope I had given you some clarity into where the sources of lack of repeatability are coming from in the course of product process development, especially in the lab scale, and also in translating the lab process to the plant. Now, if we were to generalize, a typical product process development workflow in any industry would look like something like this. Based on certain customer needs, one would have, say, a lab scale material process development, followed by a bunch of characterizations which would tell us whether what we made is right or wrong. And if they are right, then we'll take to the next step of the trials at the customer sites or at the manufacturing scale. Then once the needs are met at this scale, then we have a product. If not, we go back to the drawing board and the cycle repeats. Now, how well we understand the characterizations and their linkages to the actual final product properties is very important for making this cycle effective. If this step of material characterization and its linkage to the final product properties is not well understood, either due to poor translations of the needs into technical requirements, or not using the right methods for characterization, or not understanding the underlying physics in the course of the product process development, then we spend a lot of time in this Magenta box, where repeatedly we keep going from the lab to the more expensive steps of trials at the customer or the customer sites or manufacturing scale to verify whether what we developed in the lab is right or not. This can be pretty resource intensive and expensive, both in terms of time and the cost of the, say, the raw materials, especially if you're operating in certain niche areas like pharma. The cost of the API, etc., can be very prohibitive. On the other hand, if we were to focus on understanding the process and how it impacts the product that we produce, its properties, etc., then we should be able to focus more on this blue box and efficiently capture any misfires in our product development journey before we go through these expensive steps of, say, the trials at the customer sites or the manufacturing scale. This way, we will be able to better translate our customer needs into technical requirements, appropriately quantify the necessary properties, interactions, and improve the efficiency of our product development journey. In the next few slides, I'll share with you a case study showing how Such an approach, focusing on process understanding, can help minimize surprises during the course of, say, product development and scale up. This example is related to the scale-up of a pharmaceutical product consisting of a series of unit operations. For the purpose of this talk, though, we will focus on the scale-up of a specific unit operation, the lyophilization. For those of us that are not familiar with this area, lyophilization or freeze drying is is an important and an expensive step in the pharma and food industry, used for temperature sensitive products to increase their shelf life. Typically, here we start off with a formulation, say a drug containing formulation in a solution form, and dry off the solvent so that we obtain a free flowing powder. To accomplish this, this liquid formulation is frozen, shown here in the P and T axis. The liquid formulation is frozen, and at low pressures, applying vacuum, we sublimate off the solvent by increasing the temperature. And this way, we dry off the solvent without crossing, say, a critical temperature that the product is sensitive to. And as part of the requirements in this process, we need to be drying off the product completely without any remaining moisture, and the product should not be degraded by that is, it should not cross any of the critical temperatures that we talked about, and we had accomplished all of this in a short time. Just to give you a sense of the time, the cycle times involved here, all the upstream steps in the scale up of such kind of a pharmaceutical product would be very short. They would happen within a day or so, whereas this freeze drying lyophilization step can take a few days to a couple of weeks. So it is important that we get this scale up right the first time, so that we don't go back and forth in our trials and errors. To give you a sense for how some of these equipment look like, so the lab scale equipment may have, may have a room for storing, processing, say, 200 vials, the formulation in this, say, if you have a formulation in a vial. So we may have around 200 vials getting dried at once, whereas at the plant scale, we have, say, tens of thousands of these vials needing to get dried. And as part of the requirements, right after this lyophilization, we expect that each of these vials are dried the same way, so that there are no variations in product quality across the batch. What does it translate into in terms of requirement, say at the end of the for the end user, like a process engineer? So when we're talking about drying, what we are caring about is how you control, say, the lyophilization chamber temperature, pressure as a function of time, such that the product temperature is always staying below, say, the critical temperature that we talked about. And how do you define this lyo cycle, say, at the lab scale, and how do you translate that cycle to the plant scale? And the caveat is whatever cycle that you would have in the lab need not be appropriate for the plant, both in terms of the ability to dry off the product and the ability to optimally dry the product. So given this background, the plant scale optimization and scale up can pursue, you can consider of having, say, options like, do you want to do a DOE type of an approach at the plant, or leverage some mechanistic modeling type of first principles type of approaches. Given the challenges that we talked about in accessing plant facilities, etc., and the cost of the APIs involved, DOE at a plant scale can become very prohibitive, and typically you or your management would not want you to even consider that way. So there is a lot of science developed in this area of leveraging mechanistic models, and that's what the next slides will show how we were able to leverage that understanding with this need. To leverage the mechanistic understanding type of approaches, we need to understand how the lyophilization equipment operates. Towards that, as shown here, it consists of a chamber that houses the vials that we vials containing the formulation that we place on shelves, followed by a condenser, solvent trap, and a vacuum pump. And when the unit operates, because of the pressures, etc., that we apply and the temperatures that we provide to the shelves, the formulation, the solvent in the formulations sublimates and goes through the condenser, where part of the solvent is taken out, followed by a solvent trap, which is more relevant for a non-aqueous type of a system. And each of these units can come with limitations. For example, the condenser can only take so much of the sublimated vapors. And in this chamber, whatever shelves, whatever temperature that we are providing, whatever fluid we are providing to heat the vials, can only transfer so much of heat to the vials. So what happens at the vial scale and what happens at the overall equipment scale is something that we should be aware of to be able to effectively leverage this equipment. So this is where the need to understand the equipment characteristics and the limitations they impose comes into picture. And with that understanding of the equipment characteristics and the material properties, say the critical temperature of the formulation that we are using, and the process conditions we impose, we should be able to, through a kind of a mechanistic model, link them to the product quality, like the extent of drying, the uniformity of drying that we would get. If you think of this lyophilization in that sense as some kind of a black box, having some of the material and equipment parameter process conditions as inputs, you can relate them to the product characteristics, both in terms of, as I said, the extent of drying and the uniformity of drying. And what would that black box consist of? Can be a bunch of the underlying physical phenomena, like the phase diagrams of the solute solvent, the heat transfer characteristics, etc., and what type of vials you are using, what fill levels, condenser temperatures, etc., would go here. There is a lot of literature that captures these understandings in terms of appropriate equations so that we can quantify them. For example, these equations show how the heat input to the vial from the shelf balances the amount of solvent that can be sublimated. If you consider this as something that is occurring at the vial scale, you can expect an equipment scale physics as well to play. For example, in the lyophilization chamber, the rate at which the heat is transferred from the shelf to the vials can be different within a shelf and across the shelf. This graph shows, for example, how the within shelf variation could be of the heat transfer coefficient, and this shows how across shelves the heat transfer rate can be different. This type of information is critical to know before we actually load the lyophilizer with the expensive drug, because with this information we should be able to figure out beforehand how best to design the lyo cycle so that all the vials get dried uniformly after the cycle is complete. So with details of the material characteristics, equipment characteristics, and process parameters, the literature talks about how there is a design space over which one should be able to operate and leverage the best performance out of the lyophilizer. Awareness of these type of details helps in the scale up and site to site transfers. There are some challenges still in the industry in leveraging these type of learnings. Here is an example of the value add one can expect by leveraging process understanding type of approaches during the scale up. This box shows how when you translate a lyo process blindly from the lab scale into a plant scale lyophilizer without accounting for the changes, the type of results you get, versus by accounting for the appropriate changes using the mechanistic models, etc., and designing the plant scale lyophilizer, plant scale lyo cycle based on the lab scale lyo cycle, the type of results you'll get. So you clearly see that from 80% rejects to complete acceptance, we could achieve just by incorporating the appropriate scientific principles without having to go through multiple trials and errors. So process understanding can help us take the uncertainty out in our scale-up journeys. And some of the science behind lyophilization is such that these days, not only ensuring that there is a appropriate scale up from the lab to the plant, but also how do I optimally scale it up so that, since we talked about the lyo cycle having several days to weeks type of a cycle time, how best can we reduce the cycle time through leveraging these principles? There's a lot of literature out there that the industry can leverage, and we see some gaps and we see some opportunities in that area. In the next few slides, I'd like to spend some time providing you with some strategies that you can consider incorporating in your workflows so that you can leverage process understanding as part of your product process development efforts. The first one has to deal with investing and implementing the use of a process engineering and scale-up strategy document as part of the process development journey. We have seen that this is a routine exercise in some organizations, whereas there are some gaps in leveraging this type of a exercise in several other organizations. So we will have a brief review of what this type of an activity would involve in the next few slides, but this is definitely this can be a good value add if you have not already implemented it. The next one is, as we had seen in some of the examples that we discussed, there are a lot of equipment characterization that is needed to be understood as part of the scale-up efforts. If you can ensure that these characterizations, etc., become part of your organization's routine OQ, PQ type of protocols, that would help immensely. Because some of these access to these type of equipments, we have seen some challenges for the engineers, and hence making them as a routine exercise as part of the equipment maintenance protocols can be a good value add. Then the last one is appropriately deploying simulations or targeted experiments. For the scale-up strategy development exercise, we will consider an example case of an injectable suspension process involving, say, dispersing of API particles in a continuous phase liquid using surfactant. This may involve a mixing step, either in a batch mode or with an inline mixer, followed by filling into the syringes and storage. This process can be considered as having, say, 3 separate unit operations: a mixing, filling, and storage. So any scale-up activity would mean scaling up of each of these unit operations and understanding what are all the details involved as part of these unit operations. So as a first step in the strategy development exercise, we would want you to look at an overall process level, what are all the inputs and outputs, what are all the input parameters, be it in terms of equipment, materials, etc., that are contributing to the process, and what are the product quality attributes that come out as an output from the process. That would look like something like here. So I have an overall process, and there are these inputs in terms of both material properties like surfactant, continuous phase liquid, API particles, their size distribution, etc. The equipment geometry details, and these geometries can be in terms of the mixers, process variables, and the syringe filling machine, its geometry and process variables, and storage conditions. And the output can be in terms of, say, the drug release characteristic, shelf life. If it is an injectable suspension, you can think of as a what's the gliding force, etc., as a process product quality parameter, and dosage volume. Now, once you identify these things, the next step will be at least qualitatively vetting down how the inputs are linked to the output attributes with the best understanding of our physics. That can translate into something like this. These inputs, through some kind of a say cause and effect type of diagrams, link to the outputs. This way, at least at a higher level, we should be able to understand, well, when I introduce surfactant and continuous into the continuous phase with API particles, the surfactant liquid particle interactions, or I need to know that. Then how the API particles, for example, when they interact with the high shear mixture, how they aggregate and break, how those dynamics of those particle aggregation, etc., are linked to my surfactant behavior in ensuring that I maintain certain particle size distribution, and that is also linked to the stability and the rheology of the suspensions. And at a next level, how some of these characteristics of the suspension are playing a role in or relevant to rather in the syringe filling steps. So via, say, the suspension rheology, and also at the point of use, how the gliding force is impacted by these characteristics. So at least with this type of an activity, without getting into details, that the purpose here is to at least identify what are all the various linkages that are possible, so that we know what is it that we know, what is it that we do not know, and where to expect some surprises. And is there a way that we can mitigate knowing with this knowledge? Once that qualitative linkages are identified, then from an overall process level, we need to get into the unit operation level. So at the unit operation level, what are the inputs, outputs, and how are they interacting? For example, this would translate into the following in our case. We have 3 unit operations. At each of the unit operations, what are all the input material properties, the equipment characteristics, and the process parameters? And what are all the outputs, which could become some of the material as part of material input parameters for the next unit operation. So let's look into that with a specific unit operation like mixing in our say the injectable suspension example. So in this mixing step, we have as material properties, say, the physical properties of the liquid, the particle size distributions. Process conditions would be the mixing RPM, volume of liquid, duration of mixing. Equipment characteristics would be the geometry details of the mixing head, vessel, etc. And the quality attributes of the product would be on the lines of the output PSD and the rheology of the suspension we get. Now that we identified at the unit operation level what are all the inputs and outputs, the next step is to vet out of these inputs and outputs, which of them can be quantitatively linked to the outputs through the physics that we understand, and which cannot be linked. And that would, in our example unit operation of mixing, we may be interested in finding out how the PSD, the output PSD, is linked to the input PSD and say the shear rate and total shear. We may find that there is no, with the current understanding, there may not be a good enough model that would describe these linkages, but there is a good enough theory and good enough mechanistic approach to link the shear rate to the geometry and the process conditions. So this way we can differentiate what aspects are describable with our current understanding of our system and which aspects are not. Now that we identified, okay, these are the aspects that I can describe with some level of physics, and these are the aspects that I cannot describe. Now it's time to come up with some either experimentation, customized experimentation, or through simulations to be able to quantitatively link the inputs and outputs. In cases where we do not have that understanding via basic physics, we may be limited by needing to do only the experiments to quantitatively link the inputs and outputs. That would be translating into something like this in our mixing process. So with some understanding, we should be able to say, okay, shear rate is connected through the process to the process conditions through this kind of an equation, and the total shear also has a relationship. Now, when it comes to the particle size distribution or rheology, we may have to do actual experiments to be able to link to the process conditions like the shear rate. This is where appropriate leveraging of calculations, simulations, or experimentation, say via DOE, need to be adopted. With the quantitative linkages of the inputs and outputs through these two different modes, we should be able to, at an overall process level, connect the dots between different inputs and outputs. So starting from wherever we are, after through this kind of an exercise, we should be able to better understand our process, and maybe if there is room, we should go through this kind of iterations a couple of times to gain better understanding so that our scale-up is robust. On the aspect of the type of targeted experiments and simulations, what I want to recommend is you define the necessary experimentations appropriately and plan and devote the necessary time to do those things as part of your scale-up efforts. I would highly encourage you to consider this as not an option, but as a requirement, so that you can save a lot of time later troubleshooting. And as I already indicated, some of these equipment-related characterizations, please make sure that it becomes part of your manufacturing plant's routine maintenance or OQ type of activities. When it comes to deploying the right simulation tools for scale-up, etc., a couple of items you may want to watch out for. These are just my personal thoughts. First, I would understand the process first, catch the basic problem trying to solve, and see if a fit for purpose for your purpose model can be developed. This is where basic chemical engineering type of a talent could come. And as needed, you can consider leveraging some of the commercial simulation tools based on your application. You may find out that there may not be one tool that fits all your needs, because some of the programs may differ in the level and the type of physics they capture. And you may have to define some customized modules for your specific needs. The last and the most important thing when it comes to simulations and leveraging models is to be aware that you get what you put in. Make sure that your inputs are technically sound and you understand the assumptions of the models that you are using. Understanding the assumptions involved as part of a model and a simulation helps you to set the expectations of the value of the simulation output that you are getting for your purpose. Over the years, what we are realizing is the end user will benefit more from simulation tools that are actually customized to his or her end. In this regard, there are several players in the market that one can consider for the simulation tools. And for disclaimers, Anaga also operates in this domain. To wrap this section, here are the key takeaways that you may want to consider to incorporate process understanding as part of your product process development efforts. First, consider investing and implementing the use of a process engineering or a scale-up strategy document. Institutionalize the required equipment characterizations as part of your organization's PQOQ protocols, and appropriately deploy simulations and targeted experiments. We thank you for your participation today in this webinar, and I'm curious what kind of questions you may have. While we'll be happy to accommodate a couple of questions in this webinar, if you have any additional questions, please feel free to reach us out at contact@anagha.consulting. Again, thank you.